Looking at systems through time at repeated points in time is a fine way to estimate the amount of material in terms of carbon that is stored in forest ecosystems, and a fine way to look at how carbon changes over time in a forest landscape. But carbon exchange is much more dynamic than that. We have dynamic fluxes that are coming in and out over much shorter time periods within forest ecosystems, and they can vary tremendously from system to system to system. So, for example, we know that plants are bringing in carbon dioxide from the atmosphere and fixing it as plant biomass. So we have a certain amount of net primary productivity, and a certain amount of net primary productivity goes to above ground net primary productivity. The arrows here that are coming in from the atmosphere in this little cartoon are showing different amounts of ANPP, or above ground net primary productivity, coming into systems that are of different types. This is to represent 3 different cottonwood forests in Utah in this example. But the example holds for multiple different systems, from productive systems to less productive systems. Once that AMPP comes in, the plant will also have a strategy to allocate that AMPP below ground. So then there are further arrows going down in this graph showing total below ground carbon allocation. That is the amount of carbon that's allocated below ground. Now, carbon below ground isn't just allocated to roots, it's also allocated to mycorrhizae. So the little black arrows going to the side are showing us proportionally how much of this carbon is going into roots. And what you can see is that at the bottom of this hill, at the very bottom of this slope, we have a large amount of AMPP coming in, a large amount of carbon allocated below ground, and a small amount going to roots. This is based on some empirical measurements we took over several years in a forest on the Weber River in Utah. And then you can see an arrow going back up to the atmosphere showing efflux of CO2 back into the atmosphere. So tremendous soil CO2 efflux back into the atmosphere. When we go up to the very top, you can see ANPP coming in at a much smaller rate, a much smaller amount of carbon going below ground, but more of it is allocated to structural roots. So plants differ both in the amount of material they pull out of the atmosphere and where they put it, and that matters for the rest of the carbon flux of the system. As an aside, in the upper corner of this graph, you can see a relationship between shoot biomass and root biomass in natural forest and plantations in a study, a large study that was done to evaluate the relationship between shoot biomass to root biomass. You'll see that this graph is largely consistent with what we were talking about when we were talking about the percentage of material that is allocated, or that is below ground in terms of standing carbon of trees. This old assumption here, where we made the below ground assumption that mass is 25% of below ground mass is 25% of above ground mass. However, I also put this here to emphasize that the amount of standing material is not the same as the flux. And so the total flux rate can be relatively similar, or the flux rates can be wildly different, but the total amount of mass is not the same as the total flux into a pool at any one time. So this graph is showing those fluxes. This estimate is for the total amount of standing material. So we're talking about pools of material here, and we're talking about fluxes of material here. There are multiple ways to measure soil fluxes of CO2. And one of the most common is a chamber-based approach, where you put a chamber against the soil and then you measure, usually with infrared gas analysis, the amount of CO2 in the air, in an air volume that you sample. So these are really common units, and there are portable infrared gas analysis units that you can use to take from location to location and measure instantaneously the amount of, well, near instantaneously, the amount of CO2 that is evolving out of the soil into the atmosphere. Other methods that are a little lower tech involve the use of soda lime. Soda lime absorbs CO2 out of the air, and so placing an open container full of soda lime in a closed chamber against the soil allows you to seal off the air that would evaporate or would go into the atmosphere normally, seal it in the chamber, and allow the soda lime to absorb it. So if you put soda lime out for a known amount of time and it collects CO2 out of the air, you can weigh the soda lime before and then after your sampling. And in doing that, the weight change is related to the amount of CO2 that the soda lime absorbed, or the amount of CO2 that came into the chamber. That's a really handy method. So these are multiple methods for measuring what is commonly referred to as soil respiration. Probably more appropriately, it should be called net soil CO2 efflux, because we have efflux from the roots and we have efflux from microbial decomposition, and they're paired together. So you're not just seeing decomposition of organic residue resulting in carbon flux. You also have the roots below ground respiring, resulting in that carbon flux. And this is a measurement that's done all over the world. Another way to frame this is that this involves both heterotrophic and autotrophic sources, and both of those lead to a certain amount of net CO2 efflux. Autotrophic, of course, being plant roots, heterotrophic being microbes. In our forest network in EON, typically we have done in years where we're measuring this, we do monthly measurements. So once a month we go out and take a single measurement with a portable infrared gas analyzer, a chamber-based approach. We have to occasionally go out and pull all-nighters doing 24-hour measurements to estimate if there's a diurnal flux pattern in the data, so that we know when we measure during the day what portion of a diurnal flux we're measuring. We need to integrate these measurements with other measurements of litter fall so that we can estimate a total below ground carbon budget. Use of these infrared gas analyzers, these portable CO2 instruments, requires more skilled personnel than using something like the soda lime measurements. You need a rigorous measurement schedule. Rain, rain, snow, sleet, it doesn't matter. You have to go out and take these measurements on a regular schedule if you want a good estimate of what the system is doing. These data can be difficult to interpret and analyze. You're measuring over a very small amount of time, and you're extrapolating to a large amount of time after that. And there are some assumptions you need to check along the way to make it work. It's really appropriate for dedicated researchers who are willing to contribute data to a larger purpose over a longer time period. This is not something you do within a single quarter. This is something you have to dedicate a full year to get a full picture of how a system is fluxing, is contributing CO2 to the atmosphere from the soil environment. So this is very different than what you do with the tree measurement, because the tree measurements you can go and measure. You can walk up to a plot today that was measured in 1977. You can measure it and you can get a net change. In a course of a couple hours, you can calculate the net change from 1977 to now just by comparing values in past data. The approach with soil respiration is very different because you have to be committed to measuring it yourself over a longer period of time. Just as we found in the above ground in evergreens forest, we found a really interesting relationship where our net soil efflux rate was related to the diversity of the overstory trees. So again, kind of an interesting finding that we can layer on top of a network that's designed to measure carbon flux. So in this case, we have net soil CO2 efflux rate expressed in grams of carbon per meter squared per second. So note also, this is not units of CO2, it's units of carbon. And so note that when you're comparing this with governmental reports on carbon flux rates, sometimes it's in units of CO2 or CO2 equivalents. Here we have net CO2 efflux rate, or net carbon efflux rate. CO2 is more accurate since we're not measuring other sources of carbon. So net CO2 efflux rate compared to overstory diversity. We have two measures of overstory diversity here. We have Shannon's index and we have Simpson's index, which is another measure of diversity. So you'll recall Shannon's index incorporates both the evenness and the richness of a plant community. Simpson's does something similar. And in both cases, you can see that plots with a more diverse overstory or tree diversity have tended to have higher soil CO2 efflux rates. So just as they were more diverse, the more diverse plots were pulling in more carbon in terms of ANPP, here we're seeing they're releasing more carbon from the soil to the atmosphere. And the same can be done if we just look at overstory plant richness. To go further below, we can think about using a mini Rhizotron approach. Now, a mini Rhizotron approach is one way to look at root growth over time. So in the previous example, we're saying, hey, how much flux of CO2 is going into the atmosphere, period? How much CO2 is coming out of the soil and heading into the atmosphere? But we might have a more specific goal where we say, okay, just like above, we measured trees and we measured their change through time in terms of amount of carbon. How can we do that below ground and look at how roots are changing in terms of their amount of carbon? So sure, there's all sorts of other things a tree does other than just grow new branches and leaves, but growing new branches and leaves is a big part of it. Same for roots. Can I look at roots and just see how they change through time? Well, there are many methods for doing this, including repeat coring approaches, approaches where you put out sand in a permeable container and allow roots to grow through it, and then you sample and pull that core back out and measure the amount of roots that were produced. One of the least destructive approaches, though, is called the mini Rhizotron. And a mini Rhizotron is any sort of glass or transparent interface that is set up against the soil, allowing you to look at root growth along that transparent surface. So large Rhizotrons will be whole rooms with windows of transparent interface between the user and the soil. And there's some good examples of that out there, especially in the upper Midwest. The mini Rhizotron is a version of this. So there's the Rhizotron or the large Rhizotrons, and the mini Rhizotron is a small transparent interface. And these can take the shape of small rectangular shaped devices that are placed in soils, allowing you to insert a flatbed scanner into the soil and take images. These are very common in some other countries now. A nice cheap way to do this if you can build plexiglass boxes. A more common approach is to use a tube. So in this image here, you see a couple images here of a transparent tube. In the center image at the bottom of your screen, you see that tube buried below ground with the top painted white and the inside painted black. This is a close-up of that same image. And in this case, there's a scanner-based mini Rhizotron camera. And so in some cases, a mini Rhizotron camera uses an actual camera that takes photos along the surface of the transparent tube. And in some cases, you use a scanner. This is a scanner mounted on a motor that goes 360 degrees, and so it spins around on that motor, taking an image below ground. We have these installed at Evergreen in 10 plots. We have over 40 of these mini Rhizotrons deployed throughout our network. These are associated with measurements that when we are actively measuring root growth, we'll go out to these tubes once a month and take mini Rhizotron measurements. Generally, measurement of the images that you get from these mini Rhizotrons requires a single dedicated researcher. And so a single dedicated researcher needs to devote themselves to the measurement of roots in these plots, and then repeatedly take measurements and do the analysis so that they know what they're looking at. The image below here, if you can make this out, is one of the images we've taken in our evergreen soils, which tend to be, very dark and rooty images, much like you'd imagine below ground soils to look like. Other approaches to studying roots might involve actually digging out pits, root pits, or trenches. The problem with this approach is that it's a very destructive approach. And so once you've disturbed this environment, it's going to be a while before it recovers. And so you can measure what's there at a single point in time, but once you rebury this pit, you can't be sure that if you came back and dug it up again, you'd be looking at the same thing. So this requires sampling in different locations every time. And so this is a good way to get a standing pool And in a long succession study, you could probably look at standing pools of roots through time. But in a single ecosystem, you generally do this to see where the roots are distributed naturally, but you can't do it to watch roots change through time since there's such a big disturbance factor.